Alright, hey guys, I got a video for you on conservation of momentum. I said I would do 3 videos. I'm just going to do 1 video, and I have 3 example problems over here on this one that I'll do after I talk really quickly about this. As usual, these will be PDFs that I'll post on Schoology as well. So if you can't quite see some of these numbers and stuff, this will all be a PDF online that you can check out later for notes. Alright. So, law of conservation of momentum. Last week, or 2 weeks ago, we did egg drop stuff where we talked about how to change something's momentum, and we do that with a net force over time, which is impulse, right? Now we're going to look at situations where momentum is the same before and after in a system. So a system is more than one object that we're kind of looking at as a whole, all right? And the reason we do that is because yes, these two objects that are going to collide or whatever happens to them, we can treat them individually and see what happens to them individually. They'll change their momentum individually, but it's useful to look at them as a system, as more than one object, because the momentum is going to be the same before and after of the total system. So a system just means, if you see that word, it just means more than one object that we're treating as sort of one thing that we're looking at. The reason we do that is because if yes, there's a force between two objects when they collide, but if there's no other forces on them, there's no friction, there's no wind, there's nothing pushing from the outside besides just the force between the two objects, then the momentum of the system remains constant. That's the key to all of these types of problems that we're going to be doing. The 3 most common, or really the 3 only, I guess, but the 3 most common situations where we will use the conservation of momentum, or where the conservation of momentum will apply, is times when 2 objects bounce off of each other. And again, there has to be no external force, so that doesn't count like when an object bounces off a wall. There's an external force there, right? If we count the wall and the object as our system, well, the wall's connected to the house, which is connected to the ground, right? There's sort of, it's not an isolated system. Technically, I should have like closed, isolated system here. If you ever look it up online, it'll use the word isolated, which means there can't be a force from anything besides those 2 objects, okay? So when we talk about objects bouncing off of each other, we're talking about 2 objects that are kind of free to move on their own. They collide and they bounce off of each other. They both could be moving to start. One could be moving, stop, and hit the other one. Either way, it's 2 objects that are free to move on their own, and they collide with each other and bounce off of each other. If they bounce off perfectly, it's called an elastic collision. That means they stored all the energy in the collision and then gave it back to sort of each object. It doesn't all have to go in one object, but energy is conserved. And you looked last week at what determines whether something is a bouncy collision or whether they stick together, or it has to do with the properties of the objects that are colliding. So, but either way, if they perfectly collide, it's called an elastic collision. If they lose some energy, it's called an inelastic collision. If you see this word, like totally or completely inelastic, that means the objects stick together after they collide. Hey Russell, can you stop chewing a water bottle in my video, please? Hey, come here, you want to say hi? Russell, come. Russell, come here. Hey. He doesn't want to come over here. He stopped chewing the water bottle, though. Alright, so if you see the word totally inelastic collision or completely inelastic collision, that means that the 2 objects collide and they lost a bunch of energy. Now, they'll still have the same momentum before and after. That's kind of confusing, but they end up sticking together after. They lose the most energy they possibly could. They didn't spring back apart. They just stick together. All right. Now, momentum is still conserved in this case. It's just that they lost energy. All right. And then the third type of problem that we will apply this conservation of momentum to is called recoil. Sometimes they're called like explosions. It's whenever 2 things start together and push apart. All right. So I have 3 just example problems over here. They're probably a lot like some of the example problems that you saw in the quizzes and the CK12 assignment. So I'm going to go through these three quickly. We'll just do it all in one video, and then you'll have an example problem to work off of for any type of problem that you run into. All right. In all three of these problems, the conservation of momentum is going to apply, which means that if I'm solving this problem, I see, okay, a 2 kilogram ball hits a 1 kilogram ball, bounces off. The 1 kilogram ball speeds up, which means this object, what we can think about it as, gave some momentum to this one. So that one speeds up. We don't know how fast this one's going after. We don't know if it stops and gives all of its momentum to the 1 kilogram ball, if it gives some and is still going. Maybe it bounces off and is going backwards. Okay, so positive and negative numbers are going to be important here. Momentum is a vector. We'll get to that, I think, down in this one. I could have made this one have a negative, but this one will talk about negative velocities. But either way, anything traveling to the left, you have to make sure we put a negative there. Okay, but anyway, we don't know how much or what exactly is going to happen, but the thing we know is that the momentum initial total on this side, and the reason I have a little arrow here is because of that. If you ever see an arrow above, that just means it's a vector, and positive negatives are going to be important. So I do like to draw an arrow above my P there. So momentum initial equals momentum final. For all of these problems, there are going to be sometimes 4 velocities and 2 different masses, maybe even a third mass number. It's really important to keep your problem organized. Okay, this is why I always draw a dotted line down the middle of these. Anything that's happening before the collision, I write that over on the left side of the dotted line. Any number that they're talking about is happening after the 2 things collide or push off of each other, I'm writing on this side. That way I never, like there's this velocity, this. There are 4 different velocities. It's really easy to get them mixed up. It's not just read the problem, pick one equation, and there's only one velocity, so you plug that in there. There are 4 different ones. So it's really important to keep our problem organized. Anything that's happening before the collision, these numbers I keep over here. Anything that's happening after the collision, these numbers are going to stay over here. But the equation sort of crosses both. So initial momentum equals final momentum. Now there are a couple different ways to do this. I'm going to do it one way. If another way you've seen on the other videos works well for you, that's fine too. But okay, the total momentum is going to be the momentum of this one plus the momentum of this one, right? So it's going to be P1, we'll call it, plus P2. P is momentum. I'm going to skip right to just because I don't have a lot of room to here. The momentum of this object is the mass of it times the velocity. Right, so the m1 v1 is the momentum of this. And again, it's before the collision because it's on the left side. I could write like initial as well, but that gets a lot of subscripts. I'd rather just keep it on this side as a way to organize it. m1 v1 plus the momentum of this one, which in this case is 0, but I'm going to write it. m2 v2 equals the same thing on the other side, the momentum of this one plus the momentum of this one. So we have m1 v1 after the collision plus m2 v2 after the collision over there. I should have made m1 1 kilogram and m2 2 kilograms. Oh well. Anyway, so here's our equation. If you see this, m1 initial times v1 initial plus m2 initial, v2 initial equals these 2 final, you can always start here with this equation. A lot of times after you get used to doing these problems, you don't have to start with pi equals pf, but this is the key to the problem, right? Initial total momentum equals final total momentum. All right, so let's start plugging things in. m1 times v1 is 2 times 5 plus 0. This one's not moving, so that's 0 meters per second, so anything times 0 equals the final momentum. So 2 times the thing we don't know plus 1 kilogram times 4. All right, so now we have everything except for this v right here. So 10 on the left side. The initial momentum is 10 kilograms times meters per second equals the momentum on this side. So 2 times v plus 4. Subtract 4 from both sides, and then divide by 2, we get V equals 3 meters per second. Right, just a little algebra after you get down here. Now notice, it's not the same total velocity as before, right? It's not like, okay, we had 5 meters per second, then we have 4, that means we have 1 left. It's not the conservation of velocity. It's the momentum that's the same before and after. So here we had a momentum of 10 total. 4 of it was transferred to this ball, so that leaves 6 left for this ball, right? 6 divided by 2 is 3. So you can think about it that way too. How much momentum was transferred, right? It was 10 total. 4 of it went to this one, which means there's a momentum of 6 that ball has to have. 6 divided by 2 is 3. Now, that works great for this type of problem, but when they don't bounce off, that doesn't work great. So I'm going to keep doing it this way. If you want to think about it another way, that's fine. But the way I'm going to do it is fairly universal. That will work for all of them. Starting with momentum total initial equals total momentum final, and then go from there. Okay, second problem is going to be a totally inelastic collision where they stick together afterwards. Okay, so in this case, it's like a bullet embedding in a block. That's a common type of problem. It could be something like dropping onto a cart and they move together afterwards. Anything that they move together afterwards is a totally inelastic collision. And there's going to be a trick that we can use at the end here. All right, so for this one, still, because it's a collision, total initial momentum equals total final momentum. I can find the total initial momentum by doing the same thing I did up here. 0.02 kilograms times 300 meters per second plus 1.5 times 0, that'll just be 0, equals, now over here, these two objects are moving together now. When they're moving together, there's a trick that you can do where we can add the masses together. You can only do this if two things are moving together, exactly together. They're stuck together. We can't do it if they're ever moving separately or bouncing off of each other. Then we can't add the masses. Here, because they're moving together, we can just treat it as one big object. So we have a mass of 1.5 and a mass of 0.02. So this has a total mass, I'll write capital M, of 1.52 kilograms. Now on the right side of the equation, after this totally or completely inelastic collision, we really only have one object moving. So we can just write the momentum after the collision is just that big M times the final velocity. There's really only one velocity because it's like one big object moving together. That makes this problem a little easier. We have 0.02 times 300, which is 6 kilogram meters per second. That's the total momentum to the left. And on the right, that's going to equal 1.52 times VF. All right, really quickly, 6, we divide both sides by 1.52, and that's 3.95. So a bullet going 300 meters per second has the same momentum as the bullet and block combo going 4 meters per second. That bigger mass makes a really big difference, right, in what the total momentum can be. That's why it's really unrealistic when you see like old westerns and they shoot a bullet, right, and hits somebody and they fly backwards. That's very unrealistic. Right, bullets, even though they have a lot of energy because they're moving fast, we'll talk about energy next unit, they really don't have a ton of momentum because they're so small. All right, let's go to the last one. Last one is when two things start together, I call it recoil. Two things start together and then push apart. All right? When this happens, still the total initial momentum equals the total final momentum. That's true for all of these. I wrote that first for every single one of these. All right? That's still true. Now, the total momentum before, if two things start together and push apart. Now sometimes those two things can be moving and then push apart, so they have an initial momentum. In this case, they're not moving. It's somebody just standing on a skateboard and not moving. So the total initial momentum is 0. Now, how can the total initial, if the total initial momentum is 0, that means the total final momentum is also 0. Now, how can the total final momentum also be 0, but both things are moving? It's because momentum is a vector, right? And velocity is a vector. So this velocity that we're going to get as our answer is going to be a negative number. So that just means that this one has some amount of momentum right. This one's going to have the same amount of momentum, but negative. So that when we add them both together, we get 0. So let's do that. We have the mass of the skateboard is 0.5. So m is 0.5. M times v. V is what we don't know on this one. Plus 25, that's the mass of the person, times the velocity of the person, which is a positive 0.5. For all of these up here, everything was moving to the right. So I could have wrote positive for all of these. I should. Right? Here's the only one where it really makes a difference because there's going to be positives and negatives. All right, so we just solved this equation. 0 equals this plus this, which essentially means that whatever this momentum is the same, just negative. So if I subtract, right, I solve this problem for v,